Okay, hello and welcome to today's student training for timber design in Rfem 6. My name is Gerhard Rehm. I'm responsible for product engineering based on timber design and customer support. Let's go into detail about this go-to tool. If you're interested in to ask questions, simply click on this icon with the question mark on it and ask your questions, and we will try to answer your question as soon as possible. In case there are too many questions, you will get a follow-up email afterward where we answer this question. Okay, in case of any audio settings problems, check out this button. Maybe you need to switch to your speakers or something else. Okay, so let's have a look on today's content. In the beginning, we have a really short overview of our add-ons in Rfem 6 related to timber design, and then we will go to the Rfem 6 and make some small examples. So we will not focus on huge structures today. We will focus on smaller objects where you can follow every input and you can repeat it afterwards. Okay, so the first example is a simple stress check on a floor beam. Example number 2 is about buckling design for columns. Example 3 is lateral torsional buckling on the girder, and example 4 is for a CLT design on the surface. Okay, so let's go to this first slide here. When we talk about timber design, we have this add-on called timber design, which is for designing of members and surfaces. When we talk about CLT, you additionally need this add-on multi-layer surfaces, which creates the stiffness of the CLT. So in case you want to design CLT surfaces, walls, slabs, and so on, you need those add-ons. Then there are a few older add-ons which are based on Rfem 5. Here our standalone program RX Timber, which is still valid since the Eurocode is still valid, so you can use it until the new Eurocode is introduced in maybe 2027. And this dowel type connection with steel plates to timber beams, which is available in Rfem 5 only. We try to implement a new philosophy in Rfem 6, which is not available yet, but we are working on it. Okay, then we can switch over to Rfem 6 and start with our first example. Okay, a few words about the presentation. I do not recommend modeling directly, but just watching and then repeating what was shown with the recording, which you will receive afterwards in an email. This training requires actually the Rfem 6 student training. If you have not seen it yet, you can watch it later on our website. We will not go into the theory of timber design today. That would go beyond the time frame, and I will leave that to your professors. Okay. Then, you see the new model base data dialog. That means we will enter a model name, in this case, example 1. We choose the type of model. You can select the 3D type for this example or the 2D XC plane stress type, which would also work. So I'm used to keep it as 3D, so that's why I select 3D. Okay. Then we go to the add-on tab. Here we can activate the timber design add-on. Here on the bottom you will see the multi-layer surfaces add-on. Which was presented here. Okay, we do not need any load wizard, so I did deactivate this option here. For wind and snow loads, we don't want to generate it. Okay, standard group should be changed to timber related standard group in this case to consider the correct serviceability limit state load combinations. And as you know, we talk about load duration classes, so that's why we need to select always the additional timber standard group for European standards or US standard, Canadian standard, Italian standard, Australian standard, exactly. Okay, so in this presentation, I will use the global Eurocode. That's why I do not select any national annex here. Okay, so maybe we can deactivate the member representatives because we model only a few members. That's why we do not need it. Okay, then let's start. Okay, so you know about all the navigators and the icons, I guess, from this Rfem 6 student training. That's why I will not mention any further things about that. We start creating a new member. I use this icon here on top. And each member needs a cross-section. So I will create a new cross-section. So maybe before I start, I will delete out all data to start exactly from the scratch. So a new member, and we will load a new section from the library. So all these massive one sections can be designed according to Eurocode and also according to SIA and I guess the NTC. The composite sections, massive 2, is in progress, so it's not available yet in Rfem 6 since we introduce a new philosophy to design composite sections, because we do not want to use the gamma method, which is described in Eurocode 5, which is really limited in its usage, and we will use a different approach here, and we are working on it. So, but mostly we use our rectangular section. We need a material. We open the material library, and we can use here these filters to find the correct material, or we can simply use the search. So in this case, I want to use the C24 according to European standard. That's why I enter C24 space EN, and I will get directly the material I'm looking for. Okay, then let's go to the geometry. In this case, the width is 120 millimeters and the height is 200 millimeters. If you're interested in, you can also check here the section properties. Okay, so now the beam is on the cursor. We can start, for example, here in the origin and use this black grid points. I see the unit is still in millimeter. We can change this. So I go to 3 meters, and the next one should be at 4,500 millimeters. So the second span. In this case, we simply enter 4,500 millimeters and click the enter button, and that's it. So maybe let's switch the units. So I've changed it in a previous file. That's why it's set to millimeters. I want to use meters here. Okay. Okay, so this is our rendered two-span beam. Of course, if you want to check the wireframe model, simple switch to wireframe. So this is actually what we use for our analysis. Okay. So we have this two-span beam here. We have the beams. Now we add some supports. So we will use a fixed support here on a fixed hinge support here on the left side. Okay, and we will use a sliding support at the intermediate support. I create a new support which is sliding in X, and I will apply them on node number 2 and 3. Okay, so that's it actually. We have already the load case 1, which is created as default. So let's check load case 1. So this load case 1 considers automatically the self-weight of the beam with factor 1.0. So in case you want to calculate some examples from university, mostly they do not calculate separately the self-weight. They add it into the member load directly. So in this case, you can simply deactivate this checkbox. Okay, so here you see directly, okay, this load case 1 self-weight is assigned to the action category permanent. That's why we use a load duration permanent here. Okay, we create another load case. In this case, it's imposed load 1 on span 1. Action category we will change to imposed loads category A in this case, and you will see that the load duration is changed accordingly. I will create a copy of this load case and change here from span 1 to span 2. That's only a description. You can use whatever you want. Okay. Then let's fill our load cases with loads. So in this example, I will add a new member load. So watch out, do not use the line load for members. This will not work. You need to use the member load. Of course, you can also add some nodal loads too. But for our case, we use the member loads. Okay, and we will apply a member load, in this case of 2.5 kilonewton per meter. Hit or click the member 1 and 2 and click OK, and then you will see that the load is created. Okay, then let's switch over to the imposed load. In this case, we will use 3 kilonewton per meter on the left span, and also in load case 3 on the right span. So we need to check the imposed load separately. So we cannot use one load case in this case because, of course, the imposed load is a variable load which can act on left, on right, or both at the same time. So, for example, the biggest deflection we will receive from load case 3 in this case, but the biggest bending moment we will get from load case 2 and 3. So when we check our load combinations, so we will see, or maybe we should go to the load cases and combination dialog and then go through this dialog first. Okay, so we have created our load cases. Then we will see what happens to our actions, especially important here for the imposed loads. When we check it, okay, both load cases can act simultaneously. In case we switch over to alternatively, then both load cases will not be combined. But of course, we want to consider all of them at the same time, means simultaneously. Okay, then let's switch over to design situations. Here we can define, okay, which design situation we want to check. Of course, we want to check ULS, means permanent and transient. We want to check the characteristic deformation and the quasi-permanent deformation. So it depends on the national annex. Okay, so what we can also do is we can change the combination wizard. In this case, the combination wizard is set to second order for our example, the geometrically linear analysis. So the first order is absolutely fine. Okay, then let's check our action combinations. Here we can double check which combinations will be created, and the result are the load combinations. So load combination 1 is only 1.35 times load case 1. Load case 2 is dead load and imposed load on the first span. Load combination 3 is dead load plus the self-weight dead load plus 1.5 load case 2 plus load case 3, and this one is load case 1 plus load case 3, and so on and so on. So here you see the characteristic deformation with no partial safety factors and the quasi-permanent combination, which includes also the psi values and the kdef value. So the kdef value is described here in this edit dialog for the load case classification, and here on the bottom you see which kdef value is used as default 0.6. This is, I guess, for the most national annexes the case. For softwood, of course, if you have different service classes or different kdef values, you can enter or you can change the values here. Okay, for this simplified method to consider creep. Okay, so that's it actually so far. What we can do now, we can calculate the load cases and load combinations. So I do that for the design situation 1. The design situations, they includes all load combinations as an envelope. So what that means, we can check it here. So what we see in the beginning, we see the deformation. So we see the deformation with the maximum and the minimum. That means, of course, the minimum deformation will come from that load only. It means from CO1. So when we check CO1, we should get, no, not from CO1, sorry, from, I guess, CO2 in this case, it's the 9.5 millimeter. And the maximum one, this should come from load case, load combination 4, I guess. Yes. So load on the right span. Same for the bending moment, internal forces, My. So the maximum bending moment, so the 15.55 kilonewton meter will definitely come from load case 3. And that's the case. Okay. I don't want to go in detail because this was showed at the Rfem 6 training. You receive your deformation, the internal forces, and the support reactions. So I don't want to go in detail for now. So what we do is we focus on timber design today. That's why I switch over to the timber design add-on. Here I can define what I want to check. Yeah, I will check ULS and both SLS checks. And of course, I want to design both beams. So that's the question now. Do we want to design the beams separately, or do we want to design it as one beam or one element actually? To do so, we can create a member set. So when we go to members, create member set, you see we can combine the different members to a member set. And that means we do not design 2 members, but we can design 1 member set. Okay, I click OK. And when we check the member by right-click the member, member edit, or simple double-click the member, you will see that the design properties are now on the member. You see there are some additional tabs here because of the design settings. But when we don't want to design any member, simple create a member set and overtake the design properties to this member set. So when we click OK now and go back to the members, you see this member has lost its design property because the design property is assigned to the member set. Okay, so let's go back to the member set. And here we can define some additional settings. For example, we can define which service class should be used. We can define some local section reductions. We can define effective lengths in this example for backlaying, but since floor beams are mostly never forced to fail for stability, we do not check stability for this example. We will check stability in example 2 and 3. Okay, so let's go to the design configurations. Each element, member or member set has assigned an ULS, an SLS, and a fire config. We focus on ULS and SLS design checks for today. Let's check the default setting for the ULS config. When we check it, okay, there is, for example, this option, perform stability design, yes or no. In this example, I do not want to get informed that I miss some input for stability. That's why I deactivate this setting, since I do not want to check it. Okay, there are some further settings for members and for surfaces, and also some standard parameters, which I don't want to mention today in detail. Okay, when we check the ULS config, we will see our limits from the standard. It's also dependent on the national annex, of course, but it depends on you actually, so you can define your limits manually. Okay, then let's go to the last tab. The last tab is about design supports and deflection. Since we do not design the members individually, so member 1 and 2, but the member set, we will see that the reference length for the SLS design is used for 7.50 meters. Okay, so that means when we check now, when we would leave the setting as it is now, the program would check L over 300, for example, by 7.50 meters over 300. This is of course not correct. So what we need the segment, the first segment, and the second segment. And how to consider this is by using design supports. This is design support, so I will create one at member set start. This design support is for the design of pressure perpendicular to the grain. That's option 1, and for the option 2 to create the segments for the serviceability design checks. Okay, so in this case, we want to consider the support in local Z-axis. So each element, let's go back and check the local axis system of the member. I right-click the member, local axis system of member. Each member has its own axis system. So, and in this case, we are focused on the Z-axis. So in this case, let's go back to this dialog, create a new design support. Okay, support length should be 60 millimeters here. It should act, or the width should be overtaken from the member. Support width in plus Z direction. Of course, we can switch to minus Z direction too, but in this case, the Z-axis goes downwards. We want to apply the support at the bottom side. Okay, it's not an inner support. It's a support at the edge. We could apply some shear force reduction, and we could also apply some reinforcement elements like fully threaded screws. Okay, so for the compression design perpendicular to the grain, we need to introduce this KC90 factor. For softwood and discrete support, we use this factor 1.5. So this is a user input. We want to consider it for fire design. We don't do any fire design today, but we can leave it on. And yes, we want to consider it for the deflection check. Okay, so I assign this design support to the member start. You will see this icon here on the bottom, or the symbol, and also at member end. You will see the tables are still based on one segment, but now we see it automatically detects this intermediate node. And what we will do is we create a new design support here. Length should be 140 millimeters. And in this case, it's an inner support. This information is important because it needs to know if there is the additional 30 millimeters available for the support pressure design check on both sides or only on one side. Okay, and now you see the table has been changed. Now it detects two spans. One span is for 3 meter, the other span 4 meter 50. Okay, so we can switch to local z-axis only because we have no deformation in y direction, but we can also leave it for c and y. It does not matter. Okay, so that's it for this tab. Then let's go back to the design here on the bottom. For timber design, input data. As you see, member 1 and 2 gets invalid because we do not have any design properties on it anymore. That's why we deactivated, and we want to check only member set 1. Okay, so that's it for the input, and we can simply start the analysis. Okay. So what we see here is the overview. The overview shows us what is not fulfilled. So we see section proof is not fulfilled, and also serviceability is not fulfilled. You see it here in the graphic with this red color. Area with green colors are fulfilled, and areas with highlighted with the red color, these areas are not fulfilled. So we can switch over to design ratios on members. And here we can see in detail what design checks are not fulfilled. So we have a few 0 values here. We can use this filter, show us everything which is higher than 0. Okay, so shear is fulfilled. Sorry, not shear. The design of the support means the compression perpendicular to the grain is fulfilled. The shear is fulfilled, so we have no shear issue here, but bending is not fulfilled. We can check this here in this table, or we can also check it graphically here graphically by checking. Okay, we have different options. So the first option is the default option ratio envelope. So it shows us the ratio envelope of all design values. But we can also switch to selected design checks. And in this case, maybe I want to deactivate serviceability. I want to see only the graphical representation of the ratio for ULS or only for SLS. So here we can prove the plausibility. Yes, the ratio is affine to the deformation. That's fine so far. Additionally, you can check the results for individual design checks. So for example, here, pure bending or pure shear or pure design support. This helps you to better evaluate the results. But let's go back to the table results and to the details. So in case you are interested in how the design check is done, you can simply double click this design check and you will see, okay, what is done here. It's nothing special since we do not check any stability. We will check the stability later, and then we will see that all equations are listed here. So we do not have a kind of black box like other software. You see each intermediate value, and you will be able to follow your hand calculations with that. Okay, so in this case, nothing special. We have our K mod dependent on the load. In this case, it's CO3. CO3, of course, has included imposed load and load case 1, dead load. That means the K mod value for medium term is 0.8 multiplied by our 24 Newton per square millimeters divided by the partial safety factor, and you will get the allowable stress, and the stress divided by the allowable stress gives you the ratio. Okay, that's actually all. But of course, what we can do now is we want to optimize this situation. There are two options to optimize it. You can simply add and change your cross section or your material manually here, or you can also optimize it here. For example, in the section tab dialog, here you have the option, please optimize it from the current row. For example, in this case, we want to optimize maybe the width. So we have 120 by 200, or maybe let's introduce we can optimize according to parameter b and h, but let's start with the h. So, and we go in 20 millimeter steps, and then the program tries to fulfill the design checks for ULS design only. Okay, so we see there are still red areas because this, you see, is for serviceability. So when we go back and switch to check only ULS, and then you will see that the design check is fulfilled for this. Oh, sorry, no, I did a small mistake. Yeah, I realized. Sorry. Yeah, the optimization, of course, the ULS thing was fulfilled before, I guess. That's why we don't see any change here. The problem is only that we cannot optimize according to SLS because the problem is 120 by 300. No, sorry, it's all is good. Let's check the design ratio. Yeah, it's good. It's good. Sorry. So when we check the design check again, it was optimized 120 by 300 in this case. Okay, so I'm wondering why we cannot use 120 by 280. It should also work. So I'm confused why it is not working. Let's do it manually and double check again. Strange. It works with 280 as well. Let's try it again. Maybe I have overseen something. Sorry for that. So we will optimize the height. We will start with 200 millimeter and go to 300 millimeter in steps of 20 millimeters. So we have all the sections available for optimization. And now let's recalculate. Sorry, that was my problem. We need to calculate timber design add-on again. Sorry for that. Small mistake. Okay, now we see the maximum ratio is with 0.9, and when we check design ratio by when we check the input data again, then we will see, okay, 120 by 240 is used. Yeah, so that's fine. It works as expected. Sorry, I forgot to calculate the results again. Yeah, when we add the serviceability design check, we have sorry, this one was 200 millimeters default. Sorry again. All right, calculate timber design again. Okay, so now we get the same result as before. We will see, okay, bending design check is not fulfilled. We can go back to input data and say, okay, optimize from current row, optimize the height. We start by 200 and the maximum should be 300 in 20 millimeter steps. So that's it. Click OK, and then we can calculate the result again. Now we see that the design ratio is now fulfilled for ULS, but not for SLS. So what we need to do is we need to override this section. So simple right click, use all optimized sections in model. Then we will see the section will be overwritten, and when we check it again, then we will see the real deformation with the real cross section. So this process has to be done manually. Okay, so let's check max of all design checks. Perfect. Now we have optimized it to 95% ratio, which is fine. Okay, so this is our first example. Let's switch back to our PowerPoint slides, and we will continue with our second example, the flexural buckling. Okay, I will create a new file here. So in this case, model name is example 2. And add-ons, we will activate again the timber design add-on. We leave the standard, and we can deactivate the member representatives. Okay, I will not go in detail like in the first example. So I will skip a few things, and I will not mention all settings what I will do. Or I will not describe in detail every setting what I will do. Okay, so let's switch again, standard group timber. And now we talk about buckling design. So that means when we consider or when we use a column, of course, this column normally becomes high normal force. And it can happen that it will happen that not the stress on the member is design giving or controlling, but this column can buckle out of the plane. Depends on the weak or strong axis, of course. So for this example, we will use a column with a length of 8 meters. So section 120 by 240, this is fine so far. So the length is 4 meters and 4 meters. We will have the weak axis, which is about C axis, and the strong axis, which is about Y axis. And about Y axis, about the strong axis, we will have no restraint considered, and about C axis, we will have considered a restraint here in Y direction. Okay, so we need some supports on the bottom. Oops, sorry. On the bottom. And a support on top, on column head. So we should consider the support like this, so that the normal force or the force can go into the beam. Okay, here we go. So we will define some nodal load. I use the nodal load here, 35 kilonewton dead load. Okay, and let's create a new load case for snow load. Snow, and we will switch over to this category, smaller than 1000 meters, for example. It detects short term as load duration. And when we check our load combinations, okay, let's go back to design situations. We do not want to check serviceability in this case, since we have only gravity loads. We consider only ULS. That means, dead load and dead load plus snow, according to, in this case, first order analysis is okay, since we do only an equivalent member design. So the Eurocode 5, for example, describes two methods, so the equivalent member design and an approach with second order analysis and imperfections, but we will not do this approach today. We focus on the equivalent member design. Okay, that's actually it. We will fill load case 2 snow load, and we will apply 20 kilonewton of snow load here on top. I guess I don't have to say anything about the results. It's clear. When we check our design situation, we will get the envelope of load combination 1 and load combination 2. So we are interested, of course, in the normal force. You see the top and bottom value differs a bit because of the self-weight of the beam. Yeah, so when we go to timber design now and click the calculate button, you will get informed, okay, no effective lengths are assigned. The stability design could not be performed. This is just a warning message actually. If you are fine with that, because you know this beam will not fail for buckling, then you can ignore it. But of course, in our case, it's clear this slender beam will definitely buckle out of plane, but we need to consider this fact. So when we check the results, we get only one design check, which is a pure section proof, means force by the area divided by our strength. That's all. Yeah, nothing special. Okay, so but what we want to do is we want to do stability design check according to equivalent member method. And in this case, again, we will create a member set. Oh, sorry, two members, create member set. We want to overtake the design properties again. And here we define design types. In this case, we need effective lengths. Here in this tab, we say, okay, we want to check flexural buckling about Y and Z axis. Lateral torsional buckling is not an issue. This will be in example number 3. You can leave it on or you can deactivate the checkbox. It doesn't matter since we have no bending moment on these beams. Okay, and here it's about the effective length factor. So in this case, it considers both buckling coefficients about both axes with factor 1.0. But as you remember, I said I want to consider a lateral restrain in Y direction on node number 2. And to do so, when we check the absolute values, it's 8 meters, of course. For buckling about Y axis, we want to consider 8 meters as buckling lengths for this Euler case 2. But for buckling about Z axis, we want to consider only 4 meters. And to consider this fact, we need to consider also this intermediate node or nodes. So activate this checkbox and pick here this member set or simple insert this row. Node 2 is detected automatically. And yes, I have a restraint in Y direction. You see now this brown colored supports. And yeah, this supports represents our restraints. And as you can see here, for buckling about Y, we still have one segment. And for buckling about Z axis, we have 2 segments. And here you can see buckling length for Y axis is 8 meters and for Z axis is 2 times 4 meters. Yeah, this is a simplification. It's on the safe side. In reality, the buckling length is a bit smaller since the turning points are next to the support somehow. But for practical usage, this is fine and common in practice. Okay, so that's it. We can click OK and OK again. And we can also activate this design support in Rfem directly. So we can check them here also. So maybe it's worth to deactivate the real supports, so the nodal supports, and then you see directly, okay, which effective length factor is used or which length is used for C, V axis, Y, or U axis. It helps you to see how you have to find your bracing or your lateral restraints. Okay, so that's actually it. We can start the analysis again. And we will get this warning message again because I did not deactivate the members. I can ignore it, but I want to do it proper. That's why I deactivated. And then we'll see we get this cross-section design check. Yeah. And additionally, we get this buckling design check. So let's double check this buckling design check because now we see all these equations from the standard. So first we start with the slenderness. Based on the slenderness, we will get the ratio for the slenderness, the relative slenderness. And yeah, with the slenderness, according to the Eurocode, considering imperfections, we calculate this reduction factors Kc. So it's actually nothing else than reducing the cross-section, section-proof design check by this Kc factor, in this case 0.23. So that means when I multiply this ratio 0.81, 0.801 by 0.23, I get exactly this ratio of 18% or 19%. Okay, so you're able to follow each each intermediate value, so you can compare it with the hand calculation. That should help a lot by proving the results. Okay, yeah, that's actually it for the buckling design check. And we can switch over to the next small example. Okay, let's talk about lateral torsional buckling. It's also a stability effect. So this effect comes from bending. So we remember buckling, flexural buckling, this comes from normal force, and this lateral torsional buckling comes actually from the bending moment. You can see it here on this image. You will see that the upper chord is failing in out of plate direction due to the high load. And this effect we need to consider for for girders, for example, for really slender beams normally. Okay, new file. Example 3. Timber standard. We do not need any representatives. Okay. We start with a new cross-section. In this case, 160 millimeters by 1600 millimeters. And of course, we cannot make this high beam with C24. We need to change the material to GL20 for example, to a Dlubal material. Okay, that's it. And that's it. So the beam length should be 18 meters, like this. And we will have fixed support on the left side. And then sliding support on the right side. Of course, we could also use the fixed one here because we do not have any axial loads. So therefore it does not matter. We have no normal force here. Okay, like this. Okay, with the slider here, we can increase the size of the supports. Yeah, and we will check everything with that load. So we will not add any further load cases, since when you do timber design, it's the ratio is always dependent on the load duration class. And in case of high self-weight and, for example, low snow, then snow is not controlling, but pure self-weight. So we will not add further loads. So I will add a load here. For example, I have no idea. Let's start with 8 kilonewton per meter on this girder, and let's see what's happening. Of course, the same when we run the analysis now, we will realize we will get this warning message. Hey, you have not defined any effective lengths. No stability is checked. And of course, we want to check stability, because when we check yeah, we check ULS and SLS. So you will see ULS design check section proof is is 63%. So actually it's good, but of course we need to know what is happening with this upper chord in this example. Yeah, so that's why we need to define an effective length here. We do not check flexural buckling. That's why I deactivated. Since we have no normal force, you can also leave it activated. Okay, and here I want to check lateral torsional buckling. We have three options to check it, because for lateral torsional buckling, we need to know what is the critical moment or the critical stress. Yeah, because based on this critical stress, we can check the equivalent member method. Yeah. When we go to, or let's start with the analytical equation to determine the critical bending moment or the critical stress. This comes from Eurocode chapter 633, but additional, we have some eigenvalue solver included. I will show you afterward, which helps you to consider more options instead of settings described in the Eurocode, which is really limited to uniform loads, to simple one-span beam, and so on. And this eigenvalue solver helps you by not using these tables from Eurocode 3 and have it considered in a common way to determine the critical bending moment. Okay, in this case, we start with the analytical method. And for the analytical method, we need to consider a buckling length factor according to Eurocode 5. We have this table in chapter 633. We have uniformly distributed load. That's why I select factor 0.9. So that means we have a buckling length of 18 meters multiplied by 0.9 equals 16.2 meters. Okay, that's it. Let's go maybe to the ULS settings and to member stability. Here we can double check, okay, where we have applied the load. So in this case, the load is applied on top flange, on top side. Because of course it has an effect when the load is acting on top side. It is more critical than the load is applied on the shear center or maybe on the bottom side. Okay, in the equivalent member design method, we simply modify the buckling length with 2 times the h, which is described in this table in chapter 633 in the Eurocode. Okay. All right, we can start the calculation. And of course, you will see, maybe I will deactivate ULS. I'm not interested in ULS. That's why I delete this. Checks out and focus on ULS only. And you see, okay, design check is not fulfilled anymore. Let's double check the design check. So we see, okay, this is our allowable strength, and we see this equation which comes from the Eurocode to determine the critical stress. Yeah, so we have some factors here, some stiffness, the 5% quantile values for A modulus and shear modulus, torsional constant or torsional constant, and the buckling length. So we have 18 meters beam length multiplied by the 0.9 was 16.2 plus, since the load is applied on the top side, plus 2 times 1.6 meters equals 19.4 meters. Yeah, we calculate again slenderness, and due to the approach of the Eurocode, we will get this reduction factor. So we modify or we multiply our stress design check, in this case the 63, we multiply in this case 0.63. In this case, we need to divide it. 0.63 divided by 0.24 equals 2.62, 2.65. Yeah, and this is exactly what we get. So that means without any restraint, we will not get a fulfilled design check. And in this example, of course, you mostly never have any 18-meter long beam with any restraint. Normally, there's some bracing here at the other sides and some beams added to this beam which supports it. Yeah, and this effect we want to consider. Maybe we will do the same first with the eigenvalue solver. I can maybe directly create a copy including the load. And for this beam, I will switch over to the eigenvalue solver. I create a new effective length where I check LTB by using the eigenvalue solver. Okay. So now we have two beams. One beam is checked with the analytical approach. The second one is considered by the eigenvalue approach. Okay, let's check the results. They should be quite similar, should not so differ so much. So in this case, we have 2.46 compared to 2.65. The result is the effective length here, which was considered on the safe side. So normally the buckling length is a bit smaller, but the Eurocode 5 does not uses simplifications. It's not exactly factor 0.9, but in reality it should be factor 0.885, for example. And also by adding 2 times the beam height is not perfectly correct. That's why we have different approach. If you would use the German approach from the German annex, you would get a smaller buckling length, and then this one should be nearly, or should be the same. Yeah. Okay. We should solve the problem. And what I do is we will add some restraints here for the buckling method. So let's do it. For both cases, we divide the members and add some intermediate nodes. I will add 2 intermediate nodes, but I will not divide the member. I create a member on nodes. That's also possible. I do not have to divide always the members. So I have this node on members. When we double check it, it's not a standard node, but a node on member. And what I will do is I will modify the buckling length. So in this case, we want to consider intermediate nodes, restrain in Y direction, and all elements can be considered now with factor 1, since we have nearly a constant moment distribution in between the center of the beam. So that's why I use 1.0 here. This is also common in practice. And for the, of course, it's a simplification. Yeah, it's not exact. A better result you will get with this eigenvalue solver. And here I do the same. I insert again this lateral restraints, and in this example the lateral restraints should be applied here on top side. So maybe switch over to the real view. So we have this brown colored supports which act at the shear center at the moment, but we will change this to the upper flange, and this setting will be sent to our eigenvalue solver. Yeah. Okay, now let's compare the result again. Okay, and you will see that, yeah, the eigenvalue solver shows us a result which is fine, but yeah, not the not the equivalent member design method by using this analytical equation. Yeah, this approach is too much on the safe side. We should use smaller buckling lengths in this case. So let's double check it. So we have 9 m 20 in this case. It's nothing else by dividing 18 by factor 18 divided by, we have 3 spans in this case, 6 plus 2 times 1.6 meters equals 9.2 meters. So maybe this approach is not correct. The buckling length in reality is smaller. But we do not focus on this method. We focus on this eigenvalue solver method because it gives us better results. Yeah. So let's check it. When we double click the design check, we do not see this equation to determine the critical stress analytically. We do it with this eigenvalue solver. And from the eigenvalue solver, we receive this alpha critical factor. Yeah. And multiplied this critical factor by the bending moment from this load combination, we will get our critical bending moment, and we can calculate our critical stress accordingly. Okay. Yeah, that's it so far. Maybe additional info. You can see here this additional results, mode shapes. So when you see it, this is the mode shape which is considered. Maybe we can switch over to the colored distribution, and here you can perfectly see how this upper flange is failing out of the plane. You'll see these areas here are restrained. We will have no deformations here at this location on the top chord, and and this is, in my opinion, the best way to consider these buckling effects. Of course, if it's clear, if it's a one-span beam with simple restraints and so on, of course, the analytical equation gives good results as well and can be used. But in more complex systems, I recommend to use this eigenvalue solver to detect this critical bending moment or stress. Okay, then that's it so far. And we will switch over to our last example. So we are leaving the beam design. We switch over to surface design. Okay, again, we need a new file. Example 4. And here for add-ons, we activate this multi-layer add-on. We activate timber design. We switch over to the timber standard, and that's it. We can create this file. And now you should know that CLT design in Rfem is not based on member design, but on surface design. It brings you many advantages, such as individual shapes. You can consider openings in the CLT panel and so on. Okay, but today we will do a simple CLT slab 1 meter by 8 meters. We create a new rectangular surface, and same like for members, we need a geometry. In this case, we need a thickness. We create a new thickness, and we will switch to layers. So here we can define our composition manually from the material library, or we can simply load compositions from the producers. So we have different countries or different producers from different countries implemented. So in this case, I will use Binderholz producer 140 millimeter 5-layered CLT panel. Okay, so when we overtake the settings, you will see, okay, the type comes from library. This is the material which is used. This is the thickness which is used, and this is the orthotropic direction which is used. Means the first layer is orientated in 0-degree direction, the second layer in 90-degree direction, and so on and so on. let's create a surface and check out the orientation. So 1 by 8 meters, I'm using the grid points. And when we check the local axis system, so you will see, okay, as I explained, the 0 degree direction is orientated parallel to the local x-axis of the surface. We can also show the layers here at surfaces layer directions. For example, with indices, you will see layer 1, 3, 5 is orientated in this direction, layer 2 and 4 in this direction. Or, for example, as resultant. So, and this gives you the span direction of the CLT. But of course, if you would model the surface like this, you see, okay, in this case, of course, I don't want to consider the orientation like that. What you can do is you can create a new composition where you rotate 0 and 90 degree direction. So you are able to go inside here, create a copy, and then change this to 90, 0, 90, 0, and so on. But I don't want to do it. It's much smarter to rotate the specific axis of the surface by, for example, 90 degree. Okay. All right. This is how you can control the orientation of your CLT. Okay, I will add the supports to the structure. In this case, we use simple pin supports. So maybe we can reduce this to see, okay, it's not a nodal support, it's a line support. It supports the whole line here. Okay, and now we need to define loading. We need, again, load cases for the impost load for this floor. Impost load category A, create a copy, and for span 2. Okay, we will feed the load cases now by loads. So we will consider 2.5 kilonewton per square meters for the self-weight. And for the impost load, yeah, we did not divide the surface here. We have one surface. So in this case, we cannot use the surface load, but we can use here our free rectangular load. And this free rectangular load is independent on the surface geometry. So we will apply this load here on the surface 1. Magnitude should be 2.8 kilonewton per square meters. And the area should be defined here by these 2 nodes. Okay, and now we see the load is applied only here on the left side, on the left span. We copy the load by Control C, insert the load by Control V, and we will get the load, and we simply modify the load position. Yeah, and that's it. When we talk about FEA, yeah, you should know about FE mesh, about meshing. Again, something what I cannot explain in detail today. When we create the FE mesh, you will see the default setting is 0.5 meter. This is the default setting. In general, we recommend to consider at least 3 elements over the width up to 5, 6, 7, 8 elements. There is no common answer. It depends always on your geometry. That's why I will change this to 0.2 meters in this case. Okay, so of course, consider the fact that the finer the FE mesh, the longer the calculation takes. Yeah, for bigger structures, please think about what FE mesh size you use. You can redefine locally as well. So it's not about the global setting always, but maybe simple refine only specific surfaces. Double click the surface, mesh refinement. You can activate it here and create a mesh refinement for specific surface, for specific lines, yeah, or for specific nodes. Okay, so that's it so far. Let's run the analysis. Okay, so let's check top view. And you will see here there are some really small values we are not interested in. That's why I define a filter, define, enter 0.01. Please show everything which is higher than 0.01. And what we see is we get shear in YC plane, which is our rolling shear. We check our transversal shear in XZ plane. We check the bending, and we check the deformation for characteristic and for quasi-permanent. Additionally, we can check it again here with our ratio envelope. So if you're interested in ratio envelope, keep the setting, and here you can define your own settings. So maybe only ULS or only SLS or only specific design check, only specific layer site, only specific layer material. Or you can deactivate the ratio envelope, and then you have only these checkboxes where you can check only one results. Okay, I'm not interested in this. I'm interested in the ratio envelope here. Okay, let's check a design check. So double click the design check and you will see what's happening. Nothing special. We receive the stresses directly from the solver, so they are not calculated by some analytical equations. So they come directly from our solver, and we compare our stresses from each layer side to the limit stress. Nothing special. To check the results, you can either check the stresses directly in Rfem by switching to the static analysis. Here you can, for example, say, okay, I want to consider layer side top, and let's check, for example, elastic stress component bending on top side, and you will see the stress component 5.4 Newton per square millimeters. Yeah. There's also this other option in the add-on. You can add, or you can open this result dialog where you can simply switch to design ratio. Okay, the design ratio here is extremely small. Maybe worth to go to this location where you can see the design ratio over the layers, or maybe the stresses. Again, here you can see the stress on the transversal layers or on the longitudinal layers. Since the transversal layers has no stiffness in y direction, of course, they cannot cover any stress for bending. Okay, for bending and also for shear. That's the typical shear stress distribution for CLT, and also tau YC, it's our rolling shear stress. Okay, so this is how you can evaluate the results for CLT. Of course, there would be much more to say, but time is running really quick already, and the hour is already over. I will leave it. I will leave this for now. And of course, there are much more things to talk about. I will forward you to our webinars on our website. So when you go to our website at dlubal.com, you will find many information here at our support tab. If you have any question, feel free to check out this knowledge base or this frequently asked questions. There are many information inside, and also here at news webinars, you can filter, for example, upcoming or accomplished webinars in English, and standard should be according to, for example, Eurocode 5. Activate this checkbox, and then the filter will show you all related timber specific webinars. Okay, And at the end, I simply want to go back to our PowerPoint presentation. And I will forward you. I want to, show you this slide about our, about the career page. So in case you are interested to work for Dlubal as a student, work student, or as after your university, feel free to check if there is some space. I'm sure there is some space, so feel free to visit this page, and maybe we will see us soon. Okay, then thank you very much for your time, and I wish you a nice rest of your day, and hopefully we see us soon. Goodbye.